So, welcome back. We will go on to the topic of heat. So, when we looked at the definition of thermodynamics earlier, we said it is a science that deals with energy and its conversion and also transformation. And so far we have looked at one form of energy transformation or conversion, which is essentially work. We now will look at the other form, which is heat. We said that there are two modes of energy transfer, heat and work. We have looked at work in a bit of detail. So, we will now go on to heat. And before we look at it, what we will also emphasize is which mode of energy transfer occurs depends on our choice of the system or the control volume. Based on how we choose it, the energy transfer may be either in the form of heat or in the form of work. So, heat is an interaction between a system and the surroundings, which takes place only because of a temperature difference between the two. That is how we define it. We will look at it in a little more detail in a few moments, but before that we want to emphasize that it is energy transfer across a boundary. So, that is, we do not talk of heat transfer within a system, we only talk of heat transfer between a system and its surroundings. So, it is transferred across a boundary by virtue of the temperature difference between the two systems. So, if there is no temperature difference between the system and the surroundings, there will be no net heat transfer is what we expect normally. We have all seen this experience, for example, where we have a hot cup of coffee or a hot cup of tea, we leave it out in a room which is cooler, and then it comes, the temperature of the coffee or the tea comes down. Or similarly, we have this experience where we, for example, have an ice cream which is cold and we leave it in a room which is at a higher temperature, and the temperature of this ice cream goes up. So, what we see is that spontaneous heat transfer occurs between a system and the surroundings when the two are at different temperatures. So, if the hot tea is at a different temperature compared to the surroundings, there is spontaneous heat transfer which happens. Similarly, if the ice cream is at a different temperature, it is colder than the surroundings, spontaneous heat transfer happens. And in our experience, spontaneous heat transfer always occurs from a higher temperature to a lower temperature. So, the hot tea cools down, the cold ice cream warms up. So, we see that heat is transferred from the surroundings to the ice cream or from the hot tea to its surroundings, and it is always in the direction from a higher temperature to a lower temperature. So, that is something we see, but this is in the case of spontaneous heat transfer. When discussing work, we discussed that work is a path function. It depends on how we went from one point to another. So, what we will see is that heat transfer is also a path function. It also depends on what path we take in going from one state to another. It is an occurrence, it is not a property. It is a path function, so it is not a property. Since it is something which happens when we are moving from one point to another, from one state to another, it is not something which is stored. So, it is something which happens while a process is going on. So, these are things which we also discussed in the context of work, and we see that all of them are also valid in the context of heat. So, it is a path function, it is not stored, and so on. When we discussed work, we said at a small amount of work when it happens, we call it as del W, and when we want to know what was the total work done, we would integrate it. So, similarly, when a small amount of heat is transferred, we call it as del Q. If we want to know the total amount of heat which was transferred during a process, we would integrate it from some state 1 to a state 2 along a particular path, and we would either call it 1Q2 or some books call it as Q12, but this is the value in some particular path, because we know these are path functions. We know that if we go from some point 1 to a point 2 in some path like this, let us say on a PV diagram, the heat transfer would be something. If we went in some other path like this, we know the heat transfer would be something else. If we went in some other zigzag path like this, we know the heat transfer would be something else, and so on. So, on a particular path, for example, we can call this as path A. This would be the value, which would be a different value if we went from 1 to 2 along some path B. This value of del Q would be different from this value of this Q12 along a path A would be different from Q from 1 to 2 along some other path B. we can find out the heat transferred per unit mass of the system. We call it as small q. It is not a property, it is not a so therefore it is also not a specific property because q is not a property, but this is the heat transferred per unit mass. We can write it as q by m, and if we take the rate of heat transfer, which is essentially del q by dt, in the limit of the time going to 0, we get a value which is what we call as q dash or q dot more commonly. This is what we call as the rate of heat transfer, the rate at which heat is being transferred. And like in the case of work, we have the same units. So the SI unit is a joule, which is what we most commonly use. Traditionally, the unit which was being used earlier was a calorie, and 1000 calories make a kilocalorie, and we are not really going to use that in this course because we see that if you do use heat in terms of calories and work in terms of joules, then in a lot of places you will have a conversion factor which is called as a mechanical equivalent of heat, which is about 4.2, and we would not want to keep putting that in a lot of places, and it is a little messy because we may not remember where to put it in and where not to. So, we are going to use joules more or less exclusively as the unit. The rate of heat transfer has the unit of joules per second, which is essentially watts. When discussing work, we discussed about the convention for our course. We said that if you have a system and the system does work, which would happen for example here when this piston moves, if this is our system and this expands and the piston moves to the right, we said that the work done by this work interaction for the system would be positive, work interaction for the surroundings would be negative. So, what we see is when the system does work, the work interaction is considered positive. In the case of heat, what we see is when heat goes into the system, we call that as positive. So, heat is positive when heat is transferred into the system, work is positive when work is done by the system on the surroundings. Similarly, heat transferred from the system to the surroundings, if there is heat transferred like this, that would be considered as negative, and in our convention of work, work done on the system would be considered negative. So, what we also see is that in general heat transfer leads to an increase in the temperature of the system, though this does not necessarily have to be true, as we will see later on. So, one case where we see this does not happen is, for example, when we have a phase change. So, if we have ice, the temperature of the ice is at 0 degree centigrade at normal pressure. So, if we transfer heat to this ice, it becomes water which is also at 0 degree centigrade. So, in that process we see that heat transferred to the ice, it gets converted into water, but there is no change in the temperature of the system. So, there are exceptions, but generally we expect that when there is heat transferred, if the system is rigid, we would expect the temperature to change. Before we go forward, I would like you to think about this for a moment. So, let us say we have a wooden block and a copper block. They are kept in an air conditioned room. Let us say it can also be some other block. Let us say I have a plastic block of this kind, and let us say I have some other block. Let us say I have a book. I keep them both in a room for a very long time. The question is, which is colder? Would the wooden block be colder? Would the copper block be colder? Would they be both at the same temperature? Is there enough data to answer this question? So, you should pause possibly here and think about it for a minute and see what is the answer you get. So, what we would expect is that if a block is kept in a room for a sufficiently long time, we would expect that it would be at the temperature as the same as the room. So, the copper block would have the temperature of the rest of the room. Let us say the temperature of the room is fixed. The wooden block would also have the same temperature as that of the room if the temperature is fixed. So, we would expect both of them to be at the same temperature. But what experience tells us is that if we touch the copper block, it feels colder than a wooden block which we touch. So, for example, if you go out on a cold morning and let us say you have a cycle there, you touch the steel parts of the cycle and then you touch the seat, which is typically made of plastic or rubber, they feel very different. The metallic portion feels a lot colder than the non-metallic portion. But what that tells us is that we are not very good at sensing temperatures, because what we feel is the rate of heat transfer, or how much heat is taken away from our hand when we touch a cold object, rather than the temperature of the object itself. So, even though both of them are at the same temperature, the metal having a higher conductivity takes away a lot more heat from our hand and it feels cold, whereas a plastic or a wooden object does not take away so much heat from us and it feels warmer. So, what we see is that we are not very good at sensing what the temperatures are, which means that we would need to have some kind of devices to do this. So, in order to sense temperatures or measure temperatures, what we are trying to do is have some instrument which we would put into some object whose temperature we want to measure. So, if I had a beaker of liquid whose temperature I wanted to measure, I would have some instrument which I would dip into it and try to find out what its temperature is. But then the question is that I can make these kind of devices, we call them thermometers of course. I can make my own thermometers, you make your own thermometers, and then we never know how to match them. So, one way of getting across that is to have some reference points. So, for example, I put my thermometer into a mixture of ice and water, pure ice and water, which are there at atmospheric pressure. I ask you to put your thermometer also into the same mixture. Then whatever is the reading which both of these give, we can call it some value. So, usually we call this value as say 0 degrees centigrade. But what we are assuming in this is that if I put my thermometer into this mixture and leave it long enough, my thermometer will be at the same temperature as the ice and water. If your thermometer is there long enough, it would also be at the same temperature as the ice and water, which means that each of the thermometers is at the same temperature. So, if I put these two thermometers together, there would be no heat transfer between them. And this is what is reflected in the zeroth law of thermodynamics. It says if a system A is in equilibrium with system B, for example, my thermometer A is in equilibrium with this mixture of ice and water, which is B, and system B is in equilibrium with system C. So, I have this ice and water which is also in equilibrium with this other thermometer which is C, then A and C must be in equilibrium with each other. It sort of seems fairly simple, but it essentially forms the basis of all of thermometry, because what we are usually doing is putting some system A, which is a thermometer, in equilibrium with some other system B, which can be for example this ice water, and later on we would also put this thermometer in equilibrium with some other object whose temperature we want to measure, and if that turned out to be the same as whatever we measured earlier, we know that the temperatures of both are the same.